Welcome, everyone, to On Coding Guidelines, Class Invariants, and Special Member Functions. My name is Olivia Wasalski. I've been programming in C++ professionally for 14 years. I started learning C++ 03 in 2011, so I just made it in time to see the transition between C++ before C++ 11 and after. And for the last 10 years, I've been working at Safe Software, specializing in computational geometry. We are a Canadian company that hires across Canada, and I've been told we have C++ positions opening in the next few weeks. If anyone's interested to learn more, our website is safe.com. In my role at Safe Software, I've worked with over a dozen of new C++ developers. We hire co-op students through Canadian universities. And so these are student interns that are getting paid work experience with us. For these dozen student interns, all of them have had less than a year of C++ experience. For half of them, it was their first time getting paid to write C++. And when you work with new developers, the question of what is good code comes up early. And there's a lot of different definitions of good code out there, and a lot of people have a lot of different opinions. My personal favorite was something I heard from Tony Van Erd in his CppCon 2019 talk, where Tony said, good code begets good code and works. And I love this definition. I love it so much. I love it because it cuts to the heart of the matter. I want my code to work. If it doesn't work, it doesn't matter how pretty it is, it's not good code. I also love that it doesn't place a value judgment on code. It doesn't come with any presuppositions. It's non-judgmental. Whatever works for you, if it's working, it might be good code. And then there's the first part of it. Good code begets good code. So the word beget brings forth. Does anyone have any idea of what code that begets good code could mean? Anyone brave enough? Yep. Clean APIs. Yep. Scales well. Yep. Went through a lot of reviews. Sometimes. Not always.
Flexible to change.
Flexible to change. Yep.
To focus on the begets.
Yeah.
Other people say, oh, that's good code. I want to write code like that.
Yes. So I look at this in two different ways. How to write APIs that make it easy to do the right thing and hard to do the wrong thing. But also, what code do you want blindly copy-pasted just throughout your code base? Copy-pasted and modified, because it will happen. If you have code in there, someone will copy it and paste it, even if you don't want them to. So I love this definition. But at the same time, if you give this to a new developer, it's non-actionable, because you need experience to know what is likely to work in your context. And you need experience to know what code is more likely to make other code work. And so when we're talking to new developers, that's where I believe the role of coding guidelines comes in. We need to provide something that's more actionable and more concrete and more specific than I'll know it when I see it. But when we talk about specific coding guidelines, we should come back to this. Reevaluate. Is this helping us write good code for our context? For our definition of good code. And so this talk is about the learning journey I've been on in the last 10 years. And the learning journey was kicked off by these 5 specific coding guidelines. And I have taught every single one of these guidelines to a new developer. And we're going to take these 5 specific coding guidelines and we're going to apply them one after another on the top of a simple example. And we're going to see how it's not going to be so simple anymore. We're going to explore the way special member functions interact with class invariants in C++. And as we do this, we're going to take a brief aside twice to talk about how these guidelines are influencing the design of 2 new classes in the C++ standard library, amongst many. We're going to focus on 2. And finally, we're going to teach what guidelines I currently teach today and why I teach them. So that's what this talk is about. But it's not why I'm here. It's not why this talk exists. This talk exists because I don't have the answers for you. I'm not even sure I have the answers for me. I have questions. I have questions for, are there commonly taught C++ guidelines that are incompatible in practice? What should be the role of class invariants in C++? What guidelines should you teach? What should I teach? And how do we come together as a community to write good code? Code that begets good code, and code that works. So I'm going to talk about the C++ core guidelines quite a bit. Hands up if anyone is familiar with the C++ core guidelines. That's about 2/3, 3/4 of the room. For anyone that's not familiar, they are a set of open source community guidelines where we can come together to provide guidance on how to write good code. They're meant to be widely applicable. They're meant to be across our industry, although it is known that not all these guidelines may apply to everybody. I'm going to refer to them because they're meant to be broadly applicable. I'm going to use them as such, the reference material. The other thing is I'm going to start off possibly contentious. I'm going to start off talking about exceptions. Who here works on a code base that regularly uses exceptions for error handling? Slightly less than half, and there's some nervous hands. Who here works on a code base where exceptions are expressly forbidden? 20%-ish. For the people that cannot use exceptions, don't go anywhere. There's still a lot in here for you. And when we talk about exceptions, just nod along and smile, okay? So this is C++ core guideline I-10. Use exceptions to signal a failure to perform a required task. And when you look at the C++ core guidelines on GitHub, you see something like this. They have the guideline, they have a reason. So for this one, it should not be possible to ignore an error because that could leave the system in an undefined or unexpected state. This is a major source of bugs. And at the bottom, note, an error means a function cannot achieve its advertised purpose, which includes establishing the postconditions of the function. Yeah, I'm going to move on. This is my example. It is meant to be a simple example, okay? So we have an interval struct. It's a template struct on type T. I have a low and a high value, and then I have a clamp function. I pass a T to the clamp function along with my interval, and it calls std_clamp to clamp the value between the intervals. So if the value is already between low and high, it gives you the value back. If it's less than the low value, it gives you the low value. And if it's greater than the high value, it gives you the high value. That's what std_clamp does. That's what this clamp function does. Does anyone see a way where this function could fail to establish its post conditions? Yes?
The low is higher than the high.
Yes. So this is the CPP reference page for std_clamp, and near the bottom, if low is greater than high, the behavior is undefined. Also, if nan is avoided, then T can be floating point type. So this is the error that we are going to check for and throw an exception. And that code looks something like this. Does anyone think this code is correct? Does anyone think it's incorrect? I think it's right. Even for nan, so let's take it to simple case, no nan. We check if low is less than or equal to high, then we invert that. And if that's true, if it's not less than or equal to high, we throw the error. If it is nan, if either low or high is nan, the less than or equal to return false, then you invert that returns true, you go into the if statement, you throw the error. Anyone have any objections to this?
Why we are using equals? If it's equals, we can control the separate.
Why are we using equals? It's not wrong. It's not helpful.
Yeah, you want the...
If they're equal, it's fine. If they're equal, it's fine, right? If they're equal, low and high are equal, there's a not. So if low and high are equal, the inner condition is true, and then it's not. So that's totally fine. Okay. Guideline 1 done. Keep in your minds, is this writing better code? But we're going to move on. C++ core guideline C2. Use class if the class has an invariant. Use struct if the data members can vary independently. And so this is answering the question when I define a new type. Should I use the keyword struct or should I use the keyword class? Reason, readability, ease of comprehension. Turning this into a word of power alerts the programmer that there's an invariant that they have to pay attention to, and it's a useful convention. They also then talk about what an invariant is. An invariant is a logical condition for the members of an object that a constructor must establish for the public member functions to assume. Or in other words, a class invariant is a property that is established by the constructor, assumed to be true at the start of each public member function, and re-established at the end of each public member function, which means that this property could temporarily be false within a member function, but from the outside of the class, it's always true. And this can be really useful. It can be really useful to make certain program states impossible, and that reduces our complexity. And it can also be really useful if we get to assume that the invariant is true. It can help us with performance. So going back to our struct, our interval, is there an invariant here? Can we identify one? I see some nods. I agree. There should be. So this is what the code could look like. I now have a constructor for the interval class. It's now a class. The data members are private. I pass in the low and high values, and then I do the same check. If low is not less than or equal to high, I throw the exception in the constructor. And then when I call the clamp function at the bottom, I don't have to recheck the invariant, right? It's an invariant of the class. I can assume it's true. One of the cool things about this is it moves the place the exception is thrown potentially closer to where the low and high values came from. So it might be easier to track down how we got into this state. But one of the other cool things is that if you reuse the interval over and over, you only have to check it once. And this could help with performance, depending on your use case. Phew, okay. 2 guidelines done. We're going to move on to the next one. C++ Core Guideline C20. If you can avoid defining default operations, do. Also known as the rule of 0. So this is what it looks like on the core guidelines. The reason is great. It's the simplest, and it gives the cleanest semantics. I agree, C++ core guidelines, I agree. At the very bottom, they say this is also known as the rule of 0. But we're using some interchangeable terms here. We use default operations. Partway through, we say special functions. So these are the special member functions in C++. There are 6 of them. They're functions which the compiler may automatically generate for you. They're the default constructor, copy constructor, move constructor, copy assignment operator, move assignment operator, and destructor. For the rest of this talk, I'm going to ignore the default constructor because it's not relevant. And we're going to talk about the remaining 5 as the special member functions. In all these cases, when they're generated for you by the compiler, the compiler performs a member-wise operation. So for example, if you have a class with 3 members and it has a defaulted destructor, we destroy the first member, we destroy the second member, we destroy the third member, and then we get out of there. You're right. Third, then second, then first, then we get out of there. I practiced it for the move constructor as my example, and yep, thank you. The rule of 0, this term, which I also quite love, as far as I can tell, may have been coined by R. Martino Fernandez. Thank you, R. Martino Fernandez, for giving such wonderful terminology. And I think it's best illustrated by the example on his original blog post on the matter. So for this example, we're writing a class that owns an H module resource from the Windows API. It's a handle to a loaded module, it's usually a DLL, and it must be released by passing it to the free library function. So one option is you can implement a class and you can implement the 5 special member functions for that class, and then have other module-related functions. And he points out, no, actually, you can do something simpler. If you use std unique putter here with a custom deleter, you can just ignore the special member functions, they go away. And it does the same thing as the first version, but there's no duplication of ownership logic. We don't have to mix ownership with other concerns. Less code means less opportunity for bugs, and we get better exception safety nearly for free. And so, as R. Martino Fernandez says, we have arrived at the rule of 0, which is actually a particular instance of the single responsibility principle. Classes that have custom destructors copy move constructors or copy move assignment operators should deal exclusively with ownership. Else they should not mention them and let the compiler generate them for you. So going back to our example, we're done. Yeah, we got here by accident. We don't have to make any change to follow this guideline. Phew, okay, 3 out of 5 done. We have 2 more, but here's where it's gonna get gnarly. C++ core guideline C64. A move operation should move and leave its source in a valid state. Also known as moved from objects should be in valid but potentially unspecified states. This is what the CPP core guidelines page on it says. Note, ideally, moved from should be the same as the default value for the type, but there could be exceptionally good circumstances where that is not possible or it's not worth the performance trade-offs. Set of caveats. But at the bottom, it says, always leave the move from object in a valid state. Okay. So here's our interval class. If you move from it, and so low and high t's are moved from, is the interval in a valid but unspecified state? You don't know. That's correct. Oh no, what do we do here? So for this example, if you have an interval of strings, my first interval, the low value is apple, and the high value is banana, clementine, durian, egg, fruit, fig, and you move interval A into interval B, does the invariant on interval A still hold? Does anyone think it holds? Yeah, small string optimization could come into play here. So do you think it holds? Okay. That seems like the consensus. Yeah, that seems like the consensus, but it does hold. I've tested with GCC 15.01 and Clang 20.1.0 and MSVC 19.43, 17.13. I expected this to fail, but it worked. I don't know why all 3 string implementations here are, and what's happening here is that the short string is becoming the empty string when it is moved from. I don't know why. Why we're doing these writes to these strings? Because users expect it. There may be some minor performance penalties to real programs that we're doing this. But if we have a slightly different type, now we have a pair. The first member is a string, and the second member is an int. And we move from the string, it becomes empty. Yeah, now the invariant starts failing on a move from object. So what do we do about this? This is the first guideline where I'm like, I don't have just one answer for you. There's a lot of different options we could take to follow this guideline for this example, and we're going to go through some of them together. So option 1, we can add constraints to the supported types or behavior of our interval class. So one option is we could disable the moves, and we're done. You can't move from it, you can't steal the values, and move it. You try to move from it, it just makes a copy, it's unchanged. I don't love this option, but it could be the right call for somebody. One option is we can constrain T to a set of known types that behave like we expect. So if you have visibility into all your callers, and you happen to know this is only called with arithmetic types, you could do this. And you've also solved the problem, because moving from an arithmetic type is a big copy and it does nothing. You could also do something like this to kind of be more general. So this could work if either moving from T leaves it unchanged always, or it always leaves it in an empty state. So you can add a comment. Does anyone know if it's possible to constrain a template on these conditions at compile time? At compile, yeah. I don't know how to do this. The best I could have was a comment. My boss, this was his favorite option, by the way. So that's option A, add additional constraints. We've lost the ability to have fully generic code. Let's go to option B. We could try to implement the move operations by hand to preserve the class invariant. That's a choice. We lose the single responsibility principle. We lose the rule of 0. But maybe you could argue that the single responsibility of the interval class is managing this invariant. So this was my first attempt. Remember that T is a template type. Is this correct? So instead of moving from other low, we are exchanging in something that's initialized with empty parens. It also depends on the type of T. We've also added a constraint. T needs to be default constructible or inconstructible in this way. We're also kind of assuming that two default constructed T's compare equal. I hope they do. It would be a strange type if it didn't, but that's an extra assumption we've added to our code. There's another bug here. So yeah, the bug is exceptions. If we transfer over the value of other low, and then doing the exchange on high throws an exception, even if that line of code is as well behaved as possible, we've still left our class in an invalid state again. So I've added more constraints to the type T, but they're different constraints to the ones we had the first time. For an interval class on a fully generic T, I don't know how to implement this without constraints in this way. But then I've said, okay, as long as my T is no throw default constructible and no throw move constructible and no throw move assignable, I will slap no accepts on my move operations, and then it'll be fine. And yeah, I will no longer have the ability to have intervals of std set of int, but I'm willing to make that trade-off. That's an option. So this is what the code looks like under option B. And this is what it looked like before we applied this guideline. Who here thinks that this is, if someone gave you this in code review, who here would enthusiastically approve it? Nobody. One person maybe. Depends on context. It depends. I would be slightly less enthusiastic. I'd want to ask questions. Yeah? So option C, we could weaken or abandon the class invariant, actually. So here's what weakening could look like. Oh, okay, we're going to have an extra member variable, valueless by move, because we don't know anything about T and we don't know what states we don't know what state is an empty state. And when we construct it, the constructor will either work or it won't, and it's not valueless by move. It hasn't been moved from yet. I'm going to jump to the bottom of the class. We now have an additional accessor, valueless by move, and we've weakened the class invariant for the comment. So in order for low to always be less than or equal to high, it can't be valueless by move. And then when we call clamp, we could check the valueless by move member function. We could throw an error there, or we could ignore it. And this is my implementation of what they would look like. So now we don't have the constraint that T must be no throw move constructible. We can try to handle cases where move construction and move assignment throws. Does anyone think this works? Does anyone see anything obviously wrong with it? Okay, nothing obviously wrong, even if we're not 100% convinced.
Sure, it could be made to work.
Yes.
I can't verify that your code actually.
It could be made to work even if this exact implementation has a bug. I think so too. And then also, because we've added implementations for the moves, we have to follow the rule of 5 and default the destructor, copy constructor, and copy assignment. So there's more code we have to write. So that's what this looks like. Yes?
If you have the value list by move, would
Yes.
it make sense to check that in the accessors and throw the exception there?
You could.
Rather than forcing the clamp to check that.
You could. I didn't think of that. But that is an option, absolutely.
Say it again.
So David's comment was, you could check the value list by move in the accessors and throw the exception there so that the caller doesn't have to do it. That is a good point. That is another option.
But all the other stuff.
So that's what this code looks like. And that's what we had before we applied the guideline. If someone showed up with this in code review, who would enthusiastically approve this change? Nobody. Okay, now we're going to start the first of our 2 asides into the standard library, and we're going to talk about std indirect from C++26. Some of you may think, why would anyone have a valueless by move accessor? So the stood indirect template type, it's meant to model a value with value semantics, but the value happens to be dynamically allocated, okay? And value is not empty. The value is, in the abstract sense, the value is either that it should be there. But the stood indirect template can only have no owned object if it has been moved from, and it has this extra valueless state. And so here was what the valueless after move accessor looks like. So you can query the object. And here is what the dereference operators look like. And if this is valueless, the behavior is undefined. So this is an example of code like this in action. That's the end of the aside. We're going to go back to our regularly scheduled intervals class. So yeah, the last option is we can just abandon the idea of having a class invariant. It's too hard for this type. It may not be worth it. You will know based on your context whether the effort you are putting in is worth, like you're getting enough value out of it. But you could helpfully check, the condition and construction, and you could helpfully check it again in the clam function. Yeah, so those are my options. I don't love any of them. And I could see an argument for any of them in different contexts. But let's assume that this is our context. So let's assume I have visibility into all of my colors. And I had this template, it was living its life, and now I found out about this problem. We want to have a class invariant here because there's some reason that the class invariant is buying us something that's worth it. We are willing to constrain the supported types because for our use cases, we happen to know we're using it for arithmetic types and strings. We want the requirements on the supported types to be checked with the type system. We don't want to have just a comment that people have to follow. And we want our move operations to be reasonably efficient. We don't want to make string copies if we don't have to. So for our case, we're going to settle on option B. There are real trade-offs here. The move operations may do unnecessary writes to put the move from values in empty states. Hopefully the optimizer will help in many cases to realize that those are dead writes. And we've lost the rule of zero. But maybe that's okay, My key takeaway from this is that the valid but unspecified state is not composable when building larger structures with invariants. You don't know anything about it. It's not a building block you can use to guarantee valid but unspecified states in larger systems. Okay, 4 out of 5 done. We're on the last one. And this guideline, always provide at least the basic exception guarantee. Who here has heard of the basic exception guarantee? Maybe a third of hands. This is an old term. This term has existed in our industry for a long time. It's referenced in the C++ standard. It's also, that's what it is here. So there's a section on exception safety, and there are different levels of exception safety that we have words to talk about. No throw or no fail. It never throws an exception. We're done. The strong exception guarantee means the function either succeeds, in which case it does what it said it was going to do, or if it throws an exception, everything is rolled back, so all of the inputs to the function are unchanged. A good example of this is stood vector pushback, right? If you're pushing back to the end of a vector, and that operation throws, your vector is untouched, and you can rely on that behavior. The basic exception guarantee is weaker. If the function throws an exception, the program must be in a valid state, but unspecified. Also, no resources are leaked. And all the objects invariants are intact. So they actually talk about class invariants here. And then there is an entry for no exception guarantee. The exception throws the exception. We don't know. So that's where this guideline comes in. Always give at least the basic guarantee. And so this is a blog post by Herb Sutter from 2004 on when and how to use exceptions. So he says, always give at least the basic guarantee because you need to know that errors leave your program in a valid state. He also then talks a lot more about the strong exception guarantee and when to give it. And kind of later on, he says, that's it. There is no lower level. If you don't meet the basic guarantee, it's always a program bug. Okay, strong words. Let's see if we can apply this in practice. So we're going to go through our interval class that we had from last time, and we're going to go through function by function. So for the constructor, do we think it meets the basic exception guarantee? Yes, because if it doesn't succeed, there's no object. If there's no object, there's no invariants that aren't preserved. What about our move operations that we carefully implemented by hand? They're no except. So if an exception is thrown, I don't care. Program's over. We're done. Go home. So we can skip these. They're easy. What about the destructor? Does that meet the basic exception guarantee? I heard a yes, and then I heard something over here that I didn't quite make out. It's also no except. Yes. Okay. What about the copy constructor? Yes, but if that happens, then the stack unwinds and there is no object. So there's no object whose class invariance can be violated. And the other one wasn't touched. Correct, because it was const. So yes, the copy constructor here provides the basic exception guarantee. What about the copy assignment operator? No, that is correct. And I have an example to illustrate why. So for this example, assume there's no short string optimization. Assume that all these strings are allocated on the heap. And the alphabetical order of these fruits is apple, fig, kiwi, peach. Okay? So we have A on the left and B on the right. And we are going to copy assign kiwi into apple, and that's going to succeed. And then we're going to try to copy assign peach into fig, and that could throw, because now it has to allocate a larger buffer. And we stop there, and someone catches the exception, and now interval A is left in an invalid state. The class invariants are not maintained. So do we have any tools to deal with this? I skipped ahead. Do we have any tools to deal with this? Can we implement a copy assignment operator for this class? Okay, there's something called the copy and swap idiom. And this is, again, not a new concept. So this is Herb Sutter talking about the copy and swap idiom from July 1999. And as far as I can tell, this was not new at the time. This was already established as a tool we can use. So it has two steps. One, make a copy of the object with the copy constructor. Right? If that fails, there is no object. And then if that succeeds, we are going to swap the contents of our new temporary object with this. Now, for this to work, swap must be no-fail. It must meet the no-fail guarantee. But if we do this, then we have copy assignment, and we have the strong exception guarantee. And if we have the strong exception guarantee, we have the basic exception guarantee. So that's what I've done here. I've implemented a half swap by using move assignment instead of swap, but the thinking is the same. There are disadvantages to this too. Again, I had to write more code. It's also slower, could be slower than member-wise copy assignment, because instead of potentially reusing an allocated buffer I already had, I'm now making a new one in the temporary object and swapping and deleting it. Does anyone know if we can implement a copy assignment operator for the interval class on unknown T types that is more efficient and provides the basic exception guarantee instead of the strong one? Sorry? Some bitwise operators. But what is T? It's tough. I don't know. Yeah, I don't know how to do that, so we're not going to. Now we're going to go into our second side on the C++ standard library, and we're going to talk about the flat set class from C++23. Bear in mind, this is one class from a family of types. We have a flat map and a flat multiset and a flat multimap, and they all are very similar in this way. So a flat set is a set of sorted values that are all stored in a single buffer. And because they're sorted, when you're doing a lookup operation on it, you can use a binary search. You can find it in log n. So that's the class invariant. You can also pass in as a template parameter what container type, sequence container type you would like to use. And the default is std vector, but you could pass in your own. You could have a vector with a small buffer optimization. You could have an in-place vector. That's up to you. So it's a container adapter class.
Container that adapts, for example, vector to set.
Yes. Yes. And so there is an invariant here, because if the values are not sorted, the find operation is not going to be able to perform its job in log n time. And if you look at the paper that proposed this to the standard, they're very explicit about it. So note 5, a flat set maintains the invariant that keys are sorted with respect to the comparison object. And 6, if a member function throws an exception, we will restore all the invariants to the class. We will provide the basic exception guarantee, even if it means we're clearing your object, because an empty set is a valid but unspecified state. But this is actually part of the design of this class. Now, a slide I don't have is about the special member functions for these classes. Because they're not specified in C++23, they're not mentioned. And that, to me, raised some alarm bells. If they're not mentioned, and there's a class invariant, what can I do? What can I break? So here's my example. I have this little struct. I've called him thrower. There's an int value, and you can sort on the int values. I have defaulted the destructor, the move constructor, the copy constructor, and the move assignment operator. I've implemented the copy assignment operator, and most of the time it's going to do a copy assignment, and on the third time it's called, it's going to throw. Okay? And this is the example that uses the thrower. I have a flat set of throwers 1, 2, and 3. Then I have a flat set of throwers 4, 5, and 6. And if I copy assign B into A, and I catch the exception that is thrown, does the invariant for this class hold? Standard says it must, and it does not. It does not with GCC 15.1 compiled in C++23 mode. Is this a bug? Yes, I think so. Based on the way the flat set is specified, it's a bug. Second question, who thinks we should fix this bug? Or let me invert that. Who thinks we should choose not to fix this bug? Does anyone think we should choose not to fix it? Okay, no hands. Has anyone here ever had a bug in production where an exception was thrown partway through a defaulted member-wise copy assignment operator? Then the exception was caught and handled, and you then tried to use the object, and it was in an invalid state, and you had an observable bug at the end. Has anyone ever seen this bug in production? I see 0 hands. This bug, I think, has been possible for decades. There's nothing about this that is new. And so if it could be a bug in some contexts, but it's not a bug in practice, and if fixing it could cost us performance, who now thinks we should consider not fixing this bug? Have I changed anyone's mind? 2 very reluctant hands. I don't know. I don't know what to do here. I don't have answers. So that's the end of our second aside on the C++ standard library. Yay, we've done it. We've applied all 5 guidelines to our interval example. And the code has gone from the code on the left to the code on the right. Who here would enthusiastically approve this in code review? Okay, no hands. The left one, yes, me too. Where did we go wrong? Every step of the way, it was good advice. It wasn't just well-intentioned, it was good advice in some contexts. But it didn't work here. Is it possible to have all of these things at once in C++? Can we have true class invariants? Can we have valid but unspecified states for move from objects? Can we have optimal performance? Can we follow the rule of zero? Can we write simple code? Can we catch and resolve exceptions and rely on the basic exception guarantee? And can we write fully generic code using templates? But to narrow it down even further, is it really possible to use the rule of zero and have true class invariance? And I don't know the answer. If someone has the answer, please come talk to me, either in person at this conference or leave a comment on this YouTube video. I want to know. So now we're going to get to what I currently teach. Good code depends on context. And in my context, complexity is the enemy. Our code base, I think the first line of code is either from late 93 or early 94. It was originally compiled for 16-bit systems. We had real concerns about whether we could fit a single shape in memory at once. And we have been dragging this code base into the future with us ever since to adapt to changing business needs. Some of the changes have been easy, and some have not been easy. And so when we work together on this code base, we're all a team, all of us developers. We are on a team together, and our enemy is complexity, while we adapt the code base. So that's my context. That's what good code means for me. That's what I need it to mean. So I teach the rule of zero, and I teach it enthusiastically and early for the same reason the core guidelines recommend it, because it is the simplest and provides the cleanest semantics. Now, in a different code base than mine, I think maybe I could get a void by not talking about the rule of zero. Like if all of the code already followed the rule of zero and people were doing what all the existing code did, you can maybe just not mention this because it's invisible. But my code base still has too much that looks like this. Does anyone recognize this pattern? Some, So this is the rule of three. It came before the rule of 5 and the rule of 0 for C++ before C++11. We had to implement a destructor because we owned a resource. And because we did that, the copy assignment and copy constructor would have been generated for us. We don't want it, so we've declared it ourselves. We've made it private so no one can call it. And we actually don't provide implementations for this. So if you try to use it inside the class, it's a linker error. And I want people in my code base to look at this and migrate us to this. And even better, I would love for them to use the term rule of zero in their git commit message, because it makes it really clear what they're doing. That's one of the reasons I teach the rule of zero, early and often. I also teach C++ core guideline C2, which is to use the term struct if you don't have a class invariant, and use the term class if you do. And I get asked this. I get asked all the time, should I use the struct keyword or the class keyword? It comes up every year. And every year I pull this out of my back pocket and say, let's talk about class invariants, because I have an answer for you. Bear in mind, class invariants are a tool that you can choose to apply when they are providing enough value for the complexity that they've added to your code, right? So it is a tool you can choose to use, but it may not be the tool you want in all cases. But I want to be able to write code something like this. I want to write a vector-like type. Used vector, but I want to be able to do this. I want to say I have a data pointer, and I have a size and a capacity, and I know that the size is always less than or equal to the capacity. And I know that if the capacity is 0, the data pointer is null. And I know that if the capacity is greater than 0, the data pointer has to point to something. And I want to write classes that can assume this for simplicity, but also for performance. So I do teach this guideline. I no longer teach that moved from objects should be invalid but unspecified states. What I teach instead, don't read from moved from objects. Don't do it, it's an error. If someone overwrites the moved from object with a value that's good, then you can start reading from it again. Otherwise, don't do it. And actually, it's the same as what I teach for uninitialized variables. Don't read from an uninitialized variable. It's a programming error. Same rule for move from objects. Now, this does mean it's not always easy to know. It's not always possible to know statically if your object is moved from, and it might not be easy to know if your object's moved from. And that's just the way it is. That's the world that I'm choosing to live in. Now, what's cool about this is if you combine it with the rule of 0 from before, if almost no one is writing move operations and no one is reading from move from objects, then we don't have to really talk about what the values of move from objects are. It comes up very infrequently, and so I don't. I ignore it until someone is writing a class whose sole job it is to manage ownership of a resource. And there's something going on where they can't reuse an existing library type. When that happens, I teach this. Oh, sorry, I got ahead of myself. Actually, I don't even teach this anymore. I let Clang Tidy do it for us. So there's a bug-prone use after move check in Clang Tidy. We have it turned on. It teaches them. And sometimes they ask me questions about it. And sometimes they don't, and they just fix it and move on. And that's a good day for all of us. When you are implementing a move operation, I teach these 3 things. Move from objects must be destructible, because every object is destroyed, including move from objects. I teach that a move from object must be ready to be assigned into to accept a new value. And I teach that it must be possible to take a move from object and transfer its value over into another object of the same type, as long as then you don't read that second object in a way that changes the program behavior, right? And this is required to compose well with the standard library algorithms and classes. One good example of this is the vector class. You have a vector of t's, and you move from the 5th element, the 5th object in the vector, and then you place another object at the end of the vector, and the vector needs to reallocate. It'll go ahead and it'll allocate a new buffer, and it'll place this new t in there, and then it will either copy or move all the values from the old buffer to the new one, including the move from value. Then it'll throw away that old buffer. It'll give you your new vector. So that move from object has been technically read from to be assigned over, and now you still cannot read the value from element 5. Okay, that property transfers over. What I like about these rules is they compose really well with the defaulted member-wise special member functions. So if you have a T and you are using the rule of 0, if all of your members are destructible, you are destructible. You move from members. If all of your move from members can be assigned into, you can be assigned into. And if all of your move from members can be assigned into other objects, so can you. So it composes very nicely. Okay, now we get to the tough one. I used to teach that we should provide at least the basic exception guarantee, and I wish I could still teach it, but I cannot teach it if it holds us back from using defaulted copy assignment operators. I can't do it. And then in terms of error handling in general, quoting Tony again from yesterday, it depends. I teach that different error handling strategies have different strengths and weaknesses, and which one you should use depends on the context of what you're doing and what the code around you does. Specifically, as a replacement for always provide the basic exception guarantee, I teach something slightly weaker. I still teach that you should use destructors to clean up resources. In my code, that helps us be more correct. I also teach that if you throw an exception, you should still be destructible, because the call stack is going to unwind. Your object is almost certainly going to be destroyed. If you're not destructible, we're in for real problems. And then which error handling strategy to use? They have strengths and weaknesses. It depends. Returning error codes, throwing exceptions, or just having functions with narrow contracts. I think they're all good choices that can be considered. When it comes to exceptions specifically, for my code base, what I teach is throwing it is fine. You've checked for the condition. You don't want to continue. Throw the exception. That's great. If you want to catch and handle it, it should be done with care. Because in the code base I work in, too much code does not provide the basic exception guarantee. So you have to start thinking about what operations are safe to do and what operations are unsafe. So back to why this talk exists. Are some of these commonly taught guidelines incompatible? And what role do we want to have class invariants have in C++? What guidelines do you want to teach in your code bases? What guidelines should I teach? And how do we come together to talk about writing guidelines to help us all write good code? Code that begets good code, and code that works. Thank you very much. Does anyone have any questions? I'm also willing to accept comments mailed as questions.
Hi, great talk. Thanks, by the way. At the beginning, you asked if people in their code base handle exceptions, or if they don't use exceptions at all. I'd like to propose a third alternative, which is like you use exceptions, but you don't handle them. Because we rely very heavily on RAI, and oftentimes, you don't want to just immediately terminate your program, but maybe in a much outer layer, you might want to, panic save. So, have any thoughts on that? Or
that's what my code base. That's what I teach. That's what I recommend. I think they're a good tool for that. I try to phrase my questions carefully, intentionally, because I know that there's this middle ground. I'm part of it.
Thank you.
So when you write your piece of code or you're doing a code review, how do you review it so that you're not overly paranoid to create that explosion of code? Are there certain aspects that you look for first or prioritize?
I mean, for me, I think I lean on the experience of what I've seen before, right? I know it when I see it. Do I think that this error that could theoretically happen, do I think it's likely to happen, right? And in my code base, we're willing to accept some risk because that lets us move faster, and that is good for our business. If you don't have that experience, or you're the type of person that is more risk adverse, because I work with some of those, talking to another person, hey, I'm worried about this. I also think that it might lead me down a rabbit hole where it might not be worth handling. What do we want to do? I also, in that case, like to file a ticket for it in my ticketing system. And even if all we do is close it with a comment, we've considered the risk, we're willing to accept the risk, close, we have a record of that decision that is searchable for the future.
Okay. Yeah. Thank you.
Yeah.
So, wonderful talk, thank you. John Kalb, CppCon, and I think also in C++ on C, raised the same question of moved from object, and he has the same view of you should see it as uninitialized and not as valid but unspecified.
Yeah.
I tend to agree. Others still do not, and the spec in a way is giving us troubles with that.
I wish that I could say that all objects should be valid. That would be an easier world in some places, a more satisfying world to live in. I think some of the discussion on move from objects, it's not the only way we can get into the state. That's one of the things I want to highlight, is when we're talking about whether we want to provide valid but unspecified states, that's the most common way, right? And so if we ignore exceptions and the defaulted copy assignment operator, maybe you don't throw exceptions, or it's unlikely, we could limit the conversation to move from objects. But I think there's something more here. But
thank you.
Yeah. And lots of people agree, which is why we have a client ID check for it.
Thank you. It was really great talk. In your example, so you made some, you explored some throwable, right? But there are also not only interval restrictions. So, for example, if we are using integer and send in some constant, we convert it and have overflow. So we can also throw something inside. What I mean that, do we really need to be such paranoid? Because we always can create more and more examples for what we can check in advance. But do we really need to check so many checks there? So, for example, no need to check for range. In most cases, people who are using them, they send good input. But if you are counting, from other side, if you are counting on users, sometimes then can swap and send too much, right?
Yeah. My favorite code is the simplest, personally, and I really like functions with narrow contracts in practice. So I agree with you. There's lots of cases where I would not be checking for these conditions. I would document it as a contract, it's on the caller, moving on. I want to talk about this as a tool you could choose to use in your toolbox. So there's a class that I've written that's in production that has almost a dozen member variables. There's a lot of relationships between them. It's really important that those relationships are preserved. I can see the value in reaching for some of these techniques in some use cases. And I want to be able to use those techniques when I need them. But yeah, I love functions with narrow contracts. Yeah.
I sort of want to answer that question, but building on what you said, it's good if someone is paranoid about those things and thinks about it. But that person may decide, okay, in this case, it's not worth checking, but it's always good if someone thinks about those paranoid edge cases and make sure they are handled appropriately, whatever that appropriately means in that context.
Do you see yourself using even more narrow contract functions once you can avail yourself of actual contracts in C++26?
I program a lot with design by contracts already. I use macros. So on the one hand, I'm already doing a lot of it. The thing that's going to be, I think, significantly easier for me is post conditions, because I can name the return value. So now, in order now for me to have a post condition in an assert statement in my body of my functions, I sometimes have to contort my code. And in those cases, I choose often not to write the formal post condition. I write it in a comment. And so with contracts in C++26, I see myself using especially post conditions more often. Preconditions, I just have a list of the preconditions checked at the top of my function with an assert macro today.
But narrow contracts are more about preconditions.
Yes. So I like to write functions with narrow contracts. So they have preconditions. And then I like to check them with assert macros in testing builds. So that's what I'm doing today. But, for a lot of these functions, they're not getting direct user input that hasn't been sanitized yet. These are programmer-to-programmer functions. Yeah.
Yeah, thank you very much for lots of really great insights. I have to say that I'm also a massive fan of much simpler code. So I'm kind of strongly in favor of the classes that appeared on the left originally. And one of the reasons is things change.
Yeah.
And the class on the left was pretty darn good in C++ 98, 03, 11, 14, 17. And the class on the right was not possible. I mean, some of the issues only kind of came in later. And any guideline that says, declare this trait or add this special member function, do this, it just feels error prone.
I agree. I don't think it was intentional. The guideline was moved from object should be invalid but unspecified states. I don't think the intention of the guideline was write the special member functions for all of your types by hand. I think this is an unintentional, potentially, or undesired interaction between, exceptions or moving and class invariants and special member functions, and it just is what it is.
And the other thing is almost feels like don't write classes with more than one data member.
One data member is still enough to get you into trouble.
But two, well,
One data member is still enough. So the flat set,
yeah.
the most obvious imagined implementation I have is you either have one data member that's your vector. That one data member has many parts. So you could still think of the object as having multiple parts, but there's only one data member. And just having one data member and an additional invariant around it is enough.
Yeah.
Yeah.
Thank you.
Yep.
Hi. So I guess you discussed many principles or guidelines, which are, I guess, community guidelines, and how you see there's some sort of gray area around those. How much of these have you at your company, like, how are you disseminating this information to the newer programmers? Is it through coding standards, or is it just word of mouth?
I was part of an effort to write guidelines for my company 8 years ago. And then I was under the impression that they were locked in a document and never read again. Until I was preparing for this talk. And people were like, no, I read those. So we do have some. That being said, they're not updated often. Like, we wrote them 8 years ago, and there's been almost no changes since. You know? Yeah.
Hi, great talk.
Thank you.
So we talked a lot about exception handling, exception guarantees. In our industry, we don't use exceptions that often. We use them top level. How often do you use expected, unexpected for your APIs? And do you have any thoughts, guidelines around when to use those? And maybe another lecture.
No. Yes, I do. We use stood expected. We also have some in-house error types. The issue I have was with catching the exception and resolving it. So if you have an error that you think should be handled by your immediate caller, likely, or if it's an error that you think the program as a whole should likely want to handle, I may lean towards having that part of the type system by the return of whatever mechanism you choose. And yeah, we do use stood accepted. Yeah.
We have the time for one more question. Are there any other questions?
What are your thoughts on no accept and where it's appropriate to use it?
Ooh, okay. This is an opinion. I am willing to have other people disagree. But for me, no accept was created for a very specific purpose. It was created so that algorithms and containers could query it, so they could check statically whether certain functions had the no-fail guarantee. One example is for a stood vector. If your moves are no accept, when you reallocate, you get to move your objects along. And even if you have moves implemented, but if they could throw an exception, you will make copies instead, so that you can provide the strong accepted guarantee. So I recommend putting no accept on your move constructors. And anything that is being called in a destructor, and you want to track it to make sure that you don't want an exception to be thrown in these cleanup cases, I typically don't apply it anywhere else, because in my code, it's an additional keyword. And it's adding more complexity to the signature, and some of these signatures are already very complex. But it depends, right? Your context could be different.
Thank you.
Thank you, everyone.
Thank you.